All right, it is 3 o'clock and 59 seconds, so I'm going to get started. Welcome to my talk. I like to call this talk Countman Sketch to Infinity, using probabilistic data structures to solve counting problems in .NET. Quick poll of the room. Who here has heard of Redis before? Okay, so 90% of the audience has heard of Redis. Who here has used Redis before? 80%? So we only lost about 10% of the audience. Who here has used Redis for anything more than just a cache? We have like 5 hands, which is actually 4 more hands than I thought I would have seen. So for those of you who don't know me, my name is Steve Lorello, and I am a developer advocate at Redis, and specifically I'm the .NET developer advocate, and a lot of my work sort of sits at the intersection between .NET development and Redis. And this talk in particular gets to scratch a couple of those really neat zones in my computer science brain, because we get to talk a little bit about algorithms, we get to talk a little bit about .NET, and we get to talk a bit about Redis. So this is actually a really fun talk for me. For those of you who are interested in following me, you can follow me on Twitter at @slorello. You could also follow me on GitHub at slorello89. And me and the members of my team, we have a tendency to stream pretty much weekly. You can find us at twitch.tv/Redis Inc. The repo and also the slides for this talk are all available on GitHub. So if you have a phone, you want to take a picture, and you want to come check out the code, it's right here. It's right under my username, though. So if you found me on GitHub, it's right there. It's called Probabilistic Data Structures. So before I give a talk, I usually like to go over a little bit of an agenda of what I'm going to be talking about that day. So this talk, actually another poll question. Who here has heard of a probabilistic data structure? Okay, so now we're down to about 15, I'd say 20% of the audience. So I guess we got to answer the question first. What is a probabilistic data structure? And it's actually a really interesting set of data structures that we're going to talk about today. Then we're going to go over a brief history of probabilistic data structures within the context of Redis. Now, Redis is one of those things that's a memory-first database that's known for being very performance-sensitive and very performant. And these data structures really slot in nicely to the lifeblood of Redis and really fit nicely with Redis. Then we're going to be talking about set membership problems. So we're going to get into some of the different problems that we can solve with these probabilistic data structures. The first of these is set membership, and we're going to be using Bloom filters to overcome those. Then we're going to be talking about counting problems, and specifically counting instances in large streams of data, and we're going to be using the Countman sketch to execute and count those and count those streams of data. Then we're going to look at cardinality problems, and we're going to use one of my favorite of these data structures. One of my favorite just because it's so neat, and it's really difficult to explain, so I'm going to do my best a little bit later, but it's called the HyperLogLog. And then we're going to be looking at heavy hitter problems, and we're going to be looking at the heavy keeper data structure and the algorithms surrounding that and using all of that. And of course, I have a little demo app that we're going to run, and we're going to compare the use of these data structures in Redis against some more naive approaches that you might think to use if you were just approaching these problems from the beginning. So what are probabilistic data structures? Like we saw, about 10 to 15% of the people in here had heard of a probabilistic data structure before. A probabilistic data structure, though, is a highly specialized data structure that usually answers a very specific problem and answers a very specific question about the data that we're encountering. We use probability to approximate an answer to whatever the question that we're asking is. You notice that just earlier in the agenda slide, I talked about 4 different questions that we might want to ask. And each of one of these comes up with an approximation for that answer. And we usually trade off some bit of accuracy for exponential increases in performance. Here's some examples of some probabilistic data structures, 4 of which we're going to see in this talk. Some of which we won't talk about are quotient filters, skip lists, Cuckoo filters. And these are all different data structures that exist out there in the ecosystem that you can use. They all have some problem that they answer, some problem that they solve, they have some optimization, and they usually have some trade-off, and that trade-off is almost some small bit of accuracy. It's usually in the 0.5% to 2% range. So let's just talk briefly about the history of probabilistic data structures within Redis. Now, this logo right here is actually the logo for Redis Stack, which is sort of the conglomeration of, or the pinnacle so far of probabilistic data structures within Redis. So, probabilistic data structures in OSS Redis. So the vanilla version of Redis that you just pull from Docker or you build from source in the github.com/Redis/Redis repository, sort of piqued the interest of Salvatore, who is the author of Redis, the original writer of Redis, as well as the community. And he decided to implement, well, so Redis was always this memory-first database. So memory first in that all of the stuff that goes into Redis always goes into memory first. Redis is almost always available in memory unless you're using Redis on Flash. But it's this memory first construct that's always also been performance first. We've always put a huge critical interest on performance. And because of this, and you'll see why in a little bit when I actually go over these data structures, Salvatore decided to add the HyperLogLog, which is the third one of these data structures we'll talk about, in version 2.8.9 about 8 years ago in 2014. Then we enter this new era of Redis development and Redis usage called the module API era. In version 4.0, which is 5 years ago in 2017, the OSS Redis source added what's called a module API. The module API is something that's not novel to Redis, but exists elsewhere in the ecosystem. But what it is, basically, it allows system-level developers to develop against Redis and do stuff like extend Redis, develop new data structures against Redis, and add custom commands for Redis. And then our company, Redis Inc., started to introduce some of its own modules. And one of the first ones we introduced was Redis Bloom, which was created in 2017 and adds the first of the new expanded set of these probabilistic data structures to it, Bloom, for which it's named. And then we licensed that under the Redis Source Available license, which I don't want to get too deep into the legal details here, but basically what it means is you can use it for free, just don't compete against us, and if you need to buy it, you got to buy it from us, is essentially what it comes down to, but you can pull this in and use it in your applications and build it for free. And then in 2019, we added the Top K and the Countman Sketch, which are two of the other data structures that we'll be talking about. And then in 2022, this year, we have just consolidated all of our modules, all the disparate modules of Redis, into one thing called Redis Stack, which you can just pull from Docker and use. You can build from source. You can install on your Mac. You can install from apt. It's just this new mode of interacting with Redis where we actually allow folks to bring in all of these different disparate modules and use them. So let's talk first about set membership. So set membership, we're referring to membership within a mathematical set, basically. And not a mathematical set in that it all contains numbers, but the concept of an unordered, non-duplicated set of items that we can operate against. So the question that we are asking here, the very specific question is, has a member been inserted into the set yet? So has a given element been inserted yet? So for example, say you have, this is a very common question that we ask, has a username been registered yet with our service? So let's think about some ways that we might approach this problem from a naive approach. So we just naively want to say we're going to store all of our user information in our SQL database. And then we're going to run something like this. You've probably seen something like this in the past, a select count star from users where username equals selected username, or you could even do a select one. And you just pull back the count or the username that, or the user that matches this, and you determine that, oh, that username has been added. Now, this is not really an issue if you have a relatively small set of users, but when you blow up to very large sets when you're interacting with very large sets, it becomes kind of problematic. Let's look at the access type and the time complexities of this operation real quick. So the access type is usually disk. I mean, sometimes you'll have databases that are loaded completely into memory, and you don't necessarily need to access them, access the disk, but for the most part, you're usually probably talking to your disk. And then your lookup time on this is order n, because you have to scan through all of the records that are in your database and look at each of them to essentially determine whether that username has been added yet. The good news, though, is that beyond storing your username, you don't actually have to do anything else. You don't actually have to store anything else. You're not storing any extra information other than just the users that you're actually inserting into your database. So that extra space is order 1. So now let's try to tweak this a little bit. Let's try to make it a little bit faster, right? So you might have run into a case where, oh no, this is actually taking a while because we have to scan over all of our users. Well, the next thing you probably do is you would add an index on top of your users table, right? So you would just index that username within that users table, and then you query it again. All right, great. So you would run the same query, and then, of course, we run into an interesting problem, right? So your access is still disk-based, right? But now look at your lookup time. Your lookup time is now order log n. So that's way faster, right? Order log n is next to constant, essentially, in time complexity when we're talking about, when we're discussing time complexity of algorithms. Usually, if you get something down to log n, it's usually pretty much good enough, with some rare exceptions, unless you're talking about very large numbers. But the big issue is that now we're running into this problem where, oh, we have to store all of our usernames in this other index. We have to store all of our usernames in this other index in order to do this, right? In order to construct maybe like the simple B-tree index or something like that. So the space complexity of this is now pretty vast, and when you're talking about billions of records, you're talking about many gigabytes of data that you have to store. And then you're probably accessing them through the disk, because many gigabytes of data you don't necessarily want to store readily in memory. So now let's look at the same presence problem, but using Redis, and using a similar naive approach with Redis. You can store usernames in a Redis cache, or more specifically, you might use one of the other more sophisticated data structures within Redis, for example, a set. So you would use the loneliest of Redis commands, which is the sad command, to add to the usernames set the selected username that you want to add to it. And then in order to query it, you would just use sysmembers. Sysmembers, usernames, selected username. And this is actually real fast now. So you no longer have to ever go to the disk. Your lookup time is order 1. But now we're still running into this problem where the thing that we've essentially indexed is now all stored in memory, and we're taking up this really vast amount of memory in order to store it. So enter Bloom filters. And Bloom filters are this really neat data structure. They're this specialized probabilistic data structure for performing presence checks. A Bloom filter allows you, and this is actually where the probability and the trade-off comes in. A Bloom filter allows you to definitively say whether an item has not been added to the Bloom filter yet. However, it can only probably say that an item has been added. And you'll see why as I go over an example of this. A Bloom filter uses a scheme called a k-hashes scheme, which is basically you have a group, a succession of different hash functions that you run whatever the information that you're inserting into the filter to get a single number. The stipulation here is that those hash functions have to be pretty random and uniformly distributed over the entire Bloom filter in order for this to work correctly. So all of the hash functions you're using have to have that randomness and uniform distribution over the set that you're talking to. You can represent a Bloom filter is represented as a 1D array of bits. So just a one-dimensional array of bits. all the operations that you run against it are order 1 complexity. Some people say that it's order k, but k in this case is always constant. So it's actually order 1, so it's a constant complexity. And the space is actually still order n, but instead of being order n in the size of whatever the thing that you're using is, or whatever all the data that you're inserting into it is, it's only order n in bits. And usually you essentially estimate the cardinality of your expected cardinality or size of your set, and you use between 7 and 12 bits per item that you think is going to be inserted into it. To insert an item into a Bloom filter, you just go over all of the hashes that you have, and then you index into the filter at the result of that hash function for that key that you're using, and you flip that bit in that Bloom filter to 1. And then to query it, you go over that whole filter again, and if any of them are 0, you report that no, the item has not been inserted into the Bloom filter yet. However, if every one of them is set to 1, and every single one of them is set to 1, you return that yes, the item has been added to the Bloom filter, or probably has been added to the Bloom filter, to be more accurate. So let's look at the complexities of this. Your space complexity, like I said, is still order n, but you're talking about order n in the size of the set, the actual size of the set, not the items within the set, and it's only measured in bits. Your insertion times are order 1, your lookup times are order 1, and the other trade-off is that deletes are not available within Bloom filters. So let's look at an example of a Bloom filter. So this is our Bloom filter where k equals 3, and we have a Bloom filter of size 10. Now this is a tiny Bloom filter. Like I said, you usually use 7 to 12 bits per item that you want to insert into it. So you would only really want to store 1 item in here, but for our demonstration purposes, it's actually great because it's going to show us it's actually going to show you and underline for you what the trade-off is here and how you can report false positives. So let's try to insert the username Razzle into this Bloom filter. So let's take the H1 of Razzle, so the first hash function's result of Razzle. That comes out to 2. So we take the bit at bit 2, and we flip that to 1. We'll do the same thing for H2. That comes up 5. So we flip the bit at bit 5 to 1. For H3, we do the same thing. It comes out to 8. So we flip the bit at bit 8 to 1. So now let's perform a query. Well, H1 of Fizzle, which is our next item, our next username that we want to check, is 8. Like we just saw, H3 of Razzle was 8. So that one's already 1. Okay, so that's interesting. We have a username that we know we haven't inserted yet, but we're seeing 1 here. Okay, so maybe it's has been inserted. So we take H2 of Fizzle, and that's 2. Oh boy, that one's 1 too, isn't it? Well, so maybe it's actually in there. But H4 comes out to, or H3 comes out to 4, and 4 you can see is 0. And so that 0 comes out, we see that it's not in there, and we can say definitively that it hasn't been added in there. Now the trick with these is that the instances of hash collisions are what actually produces the uncertainty behind the false positives that can be reported by a Bloom filter. And you can actually optimize these by optimizing k and optimizing the number of bits that you're using. So for false positives and tuning, like I said, this algorithm never gives you false negatives, but it can report false positives. And you can optimize the false positives when reserving the filter specifically in Redis. So in Redis, we have 3 commands that you really need to be interested in. We have bf reserve, which takes an error rate and a capacity. So you say, oh, I would like this Bloom filter to have a capacity for 40,000 members. And the error rate that I'm willing to accept here is 1%. It'll tune the Bloom filter appropriately for your use case. There's actually math behind this as well. There is a proof that was done for the original Bloom filter where basically you can optimize the k and the optimal number of bits is, like I said, somewhere between 7 and 12, depending on what the size of your set is. So real quick, I'm actually going to drop out of my slides, and I'm going to show you in the sample application that I linked you to before, and I will link you to this again at the end of the presentation. So for this sample, I took the book Moby Dick, and I parsed out all the words from it. Well, some approximation of that. Wasn't super precise with it, but I parsed out all the words from it. I inserted them into a Postgres table that was not indexed, a Postgres table that is indexed. I also inserted into a Redis sorted set, which is a slightly more advanced data structure within the open source Redis. And I also inserted into the 4 data structures that we're going to use throughout this talk. If you go into Redis Probabilistic, you will see the things that we use within Redis to actually do this. So what I'll draw your attention to, in Redis Bloom, all of the command names start with an abbreviation of whatever the data structure is. So in this case, we have BF for Redis Bloom. Right here, we're calling BF .reserve. We're passing in the name of the Bloom filter that we want to reserve, and we're passing in the error rate, which I'm saying is 1%, so 0.01, and the size of that the size of it, so 40,000. The expected capacity of it, which is 40,000. The other one I'm using here is bf.madd, which adds multiple items to the Bloom filter. bf.add just adds one item. bf.madd will add many items. And then to query the Bloom filter, all you need to do is say bf.exists, pass in your Bloom filter's name, and whatever the item is that you want to query. And if the Bloom filter thinks that it's in there, it'll report a 1. If it doesn't, it'll report a 0. Or if it knows that it's not, it will report a 0. And at the end, the stunning conclusion of this, I will run this application. You will see just what the differences are, and you'll actually see some of the errors that you'll see throughout using these kinds of data structures. Hold on. So let me just zip through these slides again. So the next one of these problems that we want to tackle are counting problems. And I'm not saying all counting problems here. There's actually a topic called combinatorics, which just is purely the study of counting problems, and we're not going to solve all of those with Redis Bloom. But counting problems, in this particular case, the counting problem I'm referring to is how many times does an individual occur in a large stream of data. So this is actually a little bit facetious to say, but this is easy to do on small to mid-size sets of data. But when you start encountering enormous data sets, this becomes very difficult. So think something like this. Think the number of views each video gets on YouTube. What are the problems with that? Well, there's billions of videos, or I think there's billions of videos on YouTube, and those videos can have 0 views to, tens of billions of views. So counting that problem becomes very difficult because you don't want it. Well, we'll get into actually why that's a huge problem. But anyway, so our first naive approach here is just to use a hash table, right? So if you're keeping a count of things and you want to access them efficiently, probably the first thing you think of is, oh, I'll just keep a hash table and just have the keys mapped to counters, and each one of those counters, I can then store the record and increment it as I see new stuff. So you have a hash table of counters. You look up the name in that hash table and increment. And instead of storing a record, you just increment it. And then on query, you just check whatever that integer is to see what the actual current count of that item is. The pro of this is that it's really straightforward. We as developers have probably all used some form of dictionary or hash set or something in our careers. They're usually pretty straightforward. They're supported in most languages. And you have guaranteed accuracy, which is real nice. The cons, though, is that the space complexity of this is really problematic. So you have an order n space complexity where n is the number of items that you're trying to count, right? And this scales pretty poorly. Think billions of records. Let's look at another naive approach for this. So say we store all of our views in a table in a SQL database, for example. And then we issue a query to a traditional relational database to search the count of all of those records. So, for example, select count star from views where name equals Gangnam Style. this is actually really a problematic query. And the reason it's problematic is because you have to scan through the entire database, check them, even if it's indexed, and then count them all up. So this is a linear time complexity operation and a linear space complexity, and it's also a linear space complexity because you have to store all of the views. And views are usually one of those ephemeral things which you really might not care to store, right? It's like, oh, this is probably superfluous data that I don't want to use. And it's not just things with like video views also. It's a lot of stuff in networking. You don't necessarily want to store everything. A lot of network communication applications have problems with this. So this is usually like not the way to go for this. So that brings us to the Countman sketch, which is actually the second one of these data structures, these probabilistic data structures we're going to talk about. This is a specialized data structure for solving this exact problem, keeping counts on very large streams of data. Similar to Bloom filters in concept, they use this multi-hash record, but instead of keeping a 1D array of bits, we have a 2-dimensional array of counters. Now, the cool thing about these Countman sketches is that they are sublinear in space complexity, and you can even make them constant. With constant time complexities for all the operations that you want to use. This never undercounts anything, but it does sometimes overcount, and you'll see why in a bit. And it's similar to the reason that we could have false positives in a Bloom filter. So to increment an item, this looks just like the last thing we were doing, right? We go from I to k, where k is the number of hashes that we have, and then in our counter table, at that I, or at that hash's result, at I, we just increment the counter. And then to query it, we just minimize over that whole set of things. So we do the same thing. We take the hash of the item that we want to check. We go through each of our rows, and we take whatever the minimum value is, and we report that minimum value as the result of our query operation. So let's take a look at a video view sketch. So we're going to answer the same question, but we're going to use a Countman sketch instead of a SQL relational table or a hash table for answering the question. So let's, for example, increment Gangnam Style, right? So H1 of Gangnam Style is 0. So we're going to just increment H1 of 0 to 1. H2 of Gangnam Style is 4. So we increment H2, 4 to 1. H3 is 6, so we increment H3, 6 to 1. Now let's look at Baby Shark. Well, Baby Shark is going to have a similar problem that we saw in the last bit, right? So H1 of Baby Shark is 0, H2 is 5, H3 is 6. So we go through and we increment each of those. But now let's try to query Gangnam Style. So H1 of Gangnam Style is 1 again, and we look and we see that the value of H1 of 0 is 2. So we're looking at the minimum of 2. Now, H2 comes out to 4, and we look and we see that H2 and 4 is 1, and then H3 is 6. So 3 and 6 is 2. So really, the question now we're asking is, what is the minimum of 2, 1, and 2? And that's 1, right? So we get the right answer at the end of this, in spite of the fact that we had hash collisions within this Countman sketch. Again, this is a intentionally tiny Countman sketch for answering the questions that we're looking at. So let's look at the complexities of this. The space complexity of this is sublinear, right? So if you have billions of records, you do not need to have billions of cells within your Countman sketch. Your increment is order 1, your query is order 1, and your delete operations, again, they're not available. For the same reason as the Bloom filters, a delete here would compromise the integrity of the sketch, so we don't expose delete operations. So the pro of a CMS is that it's extremely fast, it's super compact and sublinear, and it's a sublinear space complexity, and it's impossible to undercount. The con of a CMS, though, is that you can sometimes overcount. So when would you want to use a Countman sketch? The most appropriate times to use a Countman sketch is when you have many unique instances that you need to count, and when approximation for those instances is fine. So if anyone here works at a bank, and you would like to use accountment sketch to keep track of my bank account's balance, that's fine. But you probably don't want to use this if you have something where approximation is not okay, and you need a really precise answer. You need to think of some other way to accomplish that. So the other really useful case for accountment sketch is when your data set is very skewed. So think YouTube videos. Gangnam Style and Baby Shark have billions of views, for example, and my video on talking about accountment sketches probably only has a few dozen. Because it can be sort of a dry topic, I guess. But so just breaking real quick to go back to our code here. If we go back to Redis Probabilistic in here, you have the two methods that are you're interested in for initializing and incrementing your accountment sketch are cms.init_by_prob is actually one way to initialize a sketch. In init_by_prob, you pass in the desired error magnitude. So as a proportion of the whole set, of the cardinality of the set, the size of that set, how much error is acceptable to you, and the other bit here is what's the probability of your errors. So I set both of those to 0.01 here. There's also an init_by_dim where you can explicitly tell it to initialize your accountment sketch by a width and a depth, so that you can initialize it with whatever exact parameters that you want to tune, and you can tell it exactly how big you want it to be. And then to increment items within accountment sketch, you would just use the cms.increby and pass in the thing that you want to increment as well as the increment that you want to use. You'll see up here that I'm basically adding a list of two things, the string that I want to increment and the amount that I want to increment it by. And then to query it, all you need to do is call cms.query. You pass in the CMS's name and the word that you want to query, or the item that you want to query. In this case, it's words because we're talking about Moby Dick. So the next and one of the more interesting things to talk about here is set cardinality. So set cardinality is just counting the distinct elements inserted into a set. So what are all of the unique elements that a set has? Again, this is easier on smaller data sets. But for exact counts, you have to keep track of every single item that you've inserted into that set. And the reason for that's simple. You want to insert something into the set, and you want to determine whether you need to increment the counter or not, you need to know if the thing's already been added to the set. So this scales, kind of poorly, especially when you're talking about billions or trillions of instances. So let's think of this. Let's look at this naive approach to SQL. And I was actually talking to somebody yesterday about this exact problem, and I asked them how they would answer this question. And this was actually the query they regurgitated to me. So select count distinct ID from a particular table. So from IDs, or from views, is this example here. This is an incredibly slow operation. When the data set is unindexed, you have to sort all of the data that's in your SQL table, and then you need to scan over all the data and count the individual instances of that of each item, or count each individual instance. So the complexity for this, you're not storing anything beyond what you're already storing for whatever the data is that you're storing, right? So we're saying that this has an order 1 space complexity. That's I think that's actually kind of generous, because a lot of these instances you wouldn't want to even store some of this stuff. Querying it, like I said, is an order n log n operation. If n log n looks familiar to anybody, that's because that's usually how long it takes to sort something in the best case. And that's the overwhelming operation here, is sorting the thing. Then you have to scan over it again. So it's n log n to query in an unindexed environment. In an indexed environment, so if you've created an index, usually your data is already sorted in some way, so it's just an order n. It's an order n operation. To query an indexed is order n, or wait, I'm sorry. To query is order n. The space complexity for an index operation is order n, because you need to actually store everything again. And then insertions they're constant. They take the same amount of time as they would otherwise. So let's think of another approach to this. So let's talk about a naive approach that you might use in Redis. So you can store all these values in a sorted set or a set. Those are two data structures that exist within Redis. They've kind of been there since the beginning. They're commonly used. We talked about sets earlier. Sorted sets are another one of those same things. They're very similar. And then you can just use the Z card or the S card operation to check the cardinality of them. Card literally means cardinality. So Z card, S card, sorted set cardinality, and then that's it. But the problem is that the space complexity of this is order n. So you have to store all of the things that your entire set in memory in order to perform one of these queries. Your query is order 1, and then your insertion is either order log n or order 1, depending on whether you're using a sorted set or a set. Sorted set, it's log n. A set, it's order 1. So let's talk about the HyperLogLog, which I think is actually the neatest of these data structures, and actually was the first that was introduced to Redis in the very early days of probabilistic data structures relationship with Redis. So the HyperLogLog is a probabilistic data structure that's used to count distinct elements in a set. The space complexity of a HyperLogLog is 1. The time complexities for HyperLogLog queries and insertions are also 1. They can handle billions of records with only a few kilobytes of memory. That's right. You can actually count billions of unique records with only a couple kilobytes of data used. You're not misreading that. That's correct. And it's pretty wild that it's able to do this. So let's just walk through a HyperLogLog real quick. And this is actually the most complicated of these algorithms that I'm going to go over. So I'm going to just go over it real quick, and hopefully you'll pick up some of it. This took me a while. I had to read the white paper several times in order to understand what they were talking about. But you initialize this array of registers that's size 2 to the p. So p is some constant. It's usually 16 to 18. In Redis, we have this on the larger side. It's 18, but 16 to 18 is a traditional size of one of these. When an item is inserted, you hash that item, just like all the other instances here. We're using hashes. You determine the registered update by taking the left p bits. So whatever that constant was, you take the left p bits of that hash, and that's your register. Then you set that register to the index of the rightmost one. The rightmost one of the hash that you created, of the binary representation of that hash. The reason for this is that the probability that the rightmost one is a 1 or not, or the rightmost thing is 1 or not, scales exponentially, right? So the probability is actually exponentially small as you get further to the left, that that's the first one, that's 1. And then when you query it, you compute the harmonic mean of the registers that have been set. Not all of the registers, just the register that actually are registering a value. And then you multiply that harmonic mean by, oh, I just kicked a glass down here, sorry. You multiply that harmonic mean by some constant that's determined by the size of p. And those constants have been published out there. To insert, so let's go over an example real quick. So to insert the username bar with p equals 16, you take the hash of bar and we get this number that I'm not going to read, which is represented by this binary. So you take the first 16 bits of that and you come out with 47,357, and that's the register index. And you set that index to the index of the rightmost one. So registers sub 47,357 equals 1. Now to get the cardinality, and this is where it gets really funky, you calculate the harmonic mean of only the set registers. There's only one set register. That's calculating the harmonic mean and multiplying it by that constant, which is 0.673 for p equals 16. You compute all that, and then you call a ceiling function on that, and your result is 1, which is the answer. I mean, that's all we inserted, right? So we get 1. The remarkable thing is that all bits of this are all order 1, and like I said, with only a few kilobytes, you can count billions of records. You can keep track of billions of records, or I think even trillions, by just modifying that P just a little bit. And I'm pretty sure we use P18 just for that reason. So before I just get into the last data structure we're going to talk about, let me just show you how to use a HyperLogLog in Redis. So if you're using the Stack Exchange library, you can use HyperLogLog add async to insert the array of elements or element that you want to insert to the HyperLogLog. And then you can use the HyperLogLog length, or I think it's pf count if you're just using the raw command API. But this HyperLogLog length method, you pass in the HyperLogLog's name, and it gets you the cardinality. That's all you got to do. So the last question we're going to ask ourselves are the top elements, the heaviest flows that we're seeing in a particular stream of data. So top element flows are the most frequent elements that we encounter in a stream of data. This can be really mission critical for detecting heavy network flows, and you can just think of all sorts of really neat applications for this. So a naive approach to this might be to select by ID, or select ID from views, and then you group by your IDs, and then you order by the count of your IDs, and then you do some descending thing with a certain number of things. What that gets you is a list of your most frequent items that exist in that data set. And this is really slow, right? This is not a fast operation. Now let's think about doing this, accomplishing the same thing with Redis. So we could store all of these counts in a sorted set, or even in a hash table. Either one would work, or in a hash. Either would work. And then you just call zanchor by views 1, and then you pass in the ID. So you just continually increment all of the IDs as you encounter more of them. And then you would just do a zrev range to get the top elements. So the problem with both of these is that you have to store all the data in both of them. And in the case of the SQL table, it's really expensive from a time complexity perspective. I think it's more than order n. I think it's like probably order n log n or something to that effect. It's quite expensive to go in and query all that. But this brings us to this heavy keeper algorithm, which is we also call the top K data structure in Redis. The heavy keeper is another multi-hash strategy, and it's the last of the multi-hash strategies that we're going to be talking about today. But like many of them, they're all multi-hash, except for HyperLogLogs. They have multiple arrays with multiple counters. I'm using counters in air quotes here. And you decay smaller flows as you encounter them, and you increment larger flows. And then you use a min heap to maintain all of the top elements that you've encountered. So we have this example of a counter here. And a counter has two distinct things. The count, so in this case it's 5, and the fingerprint, which in this case is foo. To initialize a top K or a heavy keeper, you basically just take a very similar looking data structure to the HyperLogLog the Countman sketch that we talked about before. And you just initialize it, but instead of putting in a bunch of integers, you have each one of these counter like mini data structures with the 0 and whatever the fingerprint is. In this case, it's null for all of them. So top K insert at Gangnam style, we'll say that H1 is 3. So if you look at 0, 3, that's null. So we can actually increment that to, we can actually increment that to 1 and set the fingerprint to Gangnam style. The next one is 5, and so that one is also null, so we can increment that to 1. And the last one is 1, so we can increment that one to 1 and also set Gangnam style. Let's try to do the same thing with Baby Shark now. So say we encounter a collision here. Well, what do we do? Well, Baby Shark isn't what's actually in there. So we can't go ahead and necessarily increment it. So what we do is we try to decrement it. So a heavy keeper, a top K in this case, we have a probability that the item will be decayed, or an item will be decayed if you encounter a different item. So we have this deactivation function, which is just a probability, and that reports either 1 or 0. And so we'll take whatever the value that's stored in there, in this case it's 1, and we will potentially decrement it, determining based on whether or not that activation function actually happens. So let's just say, for example here, that we succeeded, and we were able to decrement that item. It decrements to 0. So because it's now 0, we can actually replace it with a new item and increment it to the correct value, which is 1. So H2 now comes out to 4. So we just increment that. And the next one, it comes out to 5, and we can increment that as well. But that 1 right there is the interesting case here. It's actually the real interesting case. And as you continue to encounter these, you'll go through one of those three permutations. Either the thing hasn't been incremented yet, so you just increment it. It has been incremented already, and you're the incrementer, so you just increment it again. Or it's been incremented, but it hasn't been incremented by the thing you're trying to insert. So you run that activation function to see if you're going to decrement it or not, and then you potentially decrement it. And if you decrement it down to 0, then you just replace it. So then to query a top K to see what the current expected flow of this thing is, we just run that same thing that we did with the count min sketch, but instead of taking the minimum, we take the maximum. We use the maximum value that we're pulling out of this. So in this case, for Gangnam Style, it's 1, so we report that it's 1. And now separately for a top K or heavy keeper in the background, we're maintaining a min heap of all the data that's been inserted into it so far. So at insertion, so when you insert a record, and this is based off of the size of the top items that you want to retrieve from here. So at insertion, you check the count of the item that you just inserted. If the min heap contains that element, you just update the count to the new count. Now, if that has been decremented several times, that might actually move the item up in the min heap and get it closer to the top. Now, if the min heap does not contain the element that you just added, you check to see if the count of the item you just added is greater than or less than the count of the min root. If it's greater than, you just replace it. Otherwise, you just ignore it. So Redis stack is, well, I guess before I do that, well, no, okay, I'll just do this first. So Redis stack, the thing I told you about earlier, which is the conglomeration of all the probabilistic data structures as well as all the other modules that Redis Inc. produces, is kind of your go-to place now for using all these probabilistic data structures, and you can use them in your applications relatively easily by spinning up a Docker image, installing it, building it from source, whatever you want to do. But now that this is sort of like the end of my slides, but I'm just going to kind of show you real quick, first the way that you can use these top Ks, and then I'm going to run this application, and I'm going to show you just what the differences are or show you how different, much more performant these data structures are, and you'll see some of the quirks that actually come up with them because we're making these trade-offs. So the top K data structure is so-called top K. It uses the heavy keeper algorithm. You call reserve on it, and you pass in a few arguments. 10 is the number of top elements you want to keep track of. 20 is the width of that structure. 10 is the depth. And then 0.925 is the probability that an item will decay if encountered, if a duplicate of a collision occurs. And then to add to a top K, you just you use top K.add, and you either insert a single item or just a list of items that you want to pass into it. And then to query the top K, if you want to find all the top elements in a top K, you just call top K.list, and that'll report all of the elements that are actually within this. So I actually have a couple of images running in Docker that I'm just going to use. And if I just run a .NET run, like I said, I have those 4 different methods. I have an unindexed Postgres database. I have an indexed Postgres database. I have our brute force Redis instance, which just uses a sorted set, because a sorted set actually can be generalized to all these problems. And I have the 4 probabilistic data structures we talked about today, Bloom filters, Countman Sketch, HyperLogLog, and Heavy Keeper, all running, all getting data inserted into them, and then we're running the different algorithms on these. So these results here that this spit out, I'm going to zoom that in for everybody. The first thing that happens here is it initializes, it flushes out the old databases and initializes new ones, and it takes all of the words from Herman Melville's Moby Dick and inserts it into each one of these different data types. Now, the interesting thing here is that the PG indexed, PG unindexed take between 3 and 4 seconds to insert, and actually the brute force method of Redis is ever so slightly slower. It takes about 4.5 to 5 seconds in my experience running this. But really, what's really cool is the probabilistic data structures only take about 700 milliseconds. So think about that's about a fifth to an eighth as long to run this, so it's a lot faster. But the speed actually isn't necessarily the improvement that we're really looking for. What's really neat, if you scroll down to the bottom of this, you'll see the different sizes of these. These sizes are all in bytes. Herman Melville's Moby Dick has 212,000 words in it. So if you're inserting these all into something that is that's an order n space complexity, it gets real expensive. So in the unindexed version of the Postgres table, we have that's 13 megabytes of data that's been inserted into it. In the index version, we have 16 megabytes. In the brute force version, for Redis, we have just under 2 megabytes of data that's inserted. And the reason for that is it's a much simpler thing that you're inserting in the table. There's no table to maintain all the overhead of, so it's much more compact. And also, the really important thing is a sorted set doesn't allow duplication. So that's just the unique items that have been added to it. But look at the sizes for our different probabilistic data structures. They're 2 orders of magnitude smaller than the other data structures that we've encountered so far. And the really cool and compelling thing is, as we grow the size of our data set, this is a mid-sized data set, but as we grow it, as we go from 200,000 to 2 million, to 20 million, to 200 million, to 2 billion, those values in the brute force records will grow, and they'll grow linearly with the set. But the rest of these, they won't grow linearly, or they won't grow nearly as linearly as these other ones, because the only one that's kind of an offender here is the Bloom filter, and that's only scaling up, 7 to 10 bits, or 7 to 12 bits per new item that's being inserted, right? And in Redis, these will actually all scale up for you with you. They will automatically expand as you insert more stuff into them. Now, let's look at the individual operations real quick. So for presence checks, all 4 times we determined that, oh, yes, the word that we were looking for, in this case, the, was present. From a time perspective, unindexed and indexed both worked pretty fast, right? So they both went, 35 milliseconds and 11 milliseconds for the indexed. That's pretty quick. Redis, we usually calculate our execution times in microseconds instead of milliseconds. And in this case, the long pull here is actually the round trip from the application through to the Redis instance, which is running locally. And the actual execution time is probably on the order of tens of microseconds. So both versions of Redis here are working really fast, 4 and 3 milliseconds. For our item count problems, so the number of times that a particular item has occurred in a set, when we use the precise versions, we all get about 14,340. We all get 14,340, which is the exact number of times that the occurs in the, which is the most common word in this data set, occurs in Moby Dick. We have a slight overcount of, about 2% in the thus from Countman sketch. And the execution time for this is much lower. It's, it's lower than the other execution times. For cardinality, you'll see that you actually have an undercount here. You have an undercount of about 1%. And with 18,391 or 931 as opposed to 18,785. Cardinality is interesting because this is actually the least performant of the SQL operation we ran. I kind of explained this before, but yeah, that can be kind of a slow operation. And then for the top Ks, 60 and 50 milliseconds for the SQL types, and then the brute force Redis, which is a log-n operation, took 7 milliseconds, and the probabilistic version, it was order 1, so it only took 2 milliseconds. So yeah, that's kind of, and these are the results. You'll see that some of them, this S keeps showing up in the top K for this one, but that's just, it's slightly off, it's ever so slightly different, but if you look and you actually interrogate this, with the exception of this S, everything else in here is the same as the other ones. And that's just based off of how that flow operates, what the probability, or what the actual decay probability was when it was encountered. So anyway, let me kind of wrap up here. If you're interested in looking at the code that I wrote for this, you can just take a picture of this QR code. That's all the data. That's all the code for this talk. My slides are in here. Instructions as to how to run the demo. You just do a Docker Compose run and a .NET run to run everything. It's pretty straightforward. Give everyone a second to do that. Take a picture. There's still people picturing. Some more resources here. My favorite resources for all things Redis is redis.io. We also have the source code. That's the same repository that I just linked you to with that QR code. And then I actually wrote a bunch of C# implementations for all of these data structures. They're available in the algorithms project. You can come check them out. I actually haven't added the Heavy Keeper yet. I'm probably going to do that next month. And again, my name is Steve Lorello. I am the .NET Developer Advocate at Redis. You can follow me on Twitter or GitHub, or every Wednesday at 2 p.m. Eastern Standard Time. I usually stream at twitch.tv/RedisInc. So yeah, and the last 2 bits of resources. If you want to learn more about Redis, we have a university for Redis called Redis University. It's at university.redis.com. And we have a Discord server that if you have any questions about Redis, usually me or a member of my team are there to answer. Come check us out at discord.com/invite/Redis. So I have time for a couple of questions, and I notice that these lights make it difficult for me to see what's going on. I'm sorry, this is just like, I can't not watch. This is too much fun. But anyway, does anyone have any questions? I'll back up so that doesn't keep bothering people. Any questions from the audience? Here we go. Go ahead. The thing is not on. I think, is the question you're asking, can you tweak the algorithms to lower your error rate?
Oh, sorry. Yeah, or just run them multiple times to 0.8%.
Yeah, so you can tweak, with all of these, as you initialize them with an expected error rate and an expected probability of error. And so you would initialize it to have the capacity, or to have the specific error rate that you want. And in Redis, what happens is Redis will automatically scale up the size of your data structure to accommodate the bits that are going on in there. Any other questions? Go ahead.
What do you do to deal with the errors that you get? With the 1% error rate?
Well, the errors are just implicit in the. So the question is, what do you do to deal with the errors that you get? So the trick is that when you're using these data structures, you are accepting that there are potential errors that occur in the system. That's why when you have, I I'm not going to fall off the stage, right? That's why when you have operations that you need precision on, that's where you really want to use these. So if you're running a bank like a bank or a stock trading thing, and you have very precise numbers or very precise operations that you're doing, you don't want to use these, but otherwise they're usually okay. I am out of time, so I'm going to pack up here while I let the other person come on. But thank you all very much for coming out. It's been great speaking to you all.